When doing my video on the capacitance between two spheres of unequal size, it occurred to me that I could tell you a little bit about two-wire transmission lines and some easy relationships to use, very important relationships that helps in computing capacitance and inductance of transmission line type structures. And I'm going to look at a two-wire transmission line. Ham radio operators used to use this type of line called an open line. Has very low loss, extremely low loss, but it's not a shielded line, so you can get radiation from it, and so it has fallen out of favor in recent years. And what it is you have two lines, two conductors, with a separation distance between them. And this is a transmission line. This will guide electromagnetic waves. And if we look at a cross-section of it, we just have two circular conductors. And they're held, they're separated with a uniform separation distance called D from center to center. And that separation distance is maintained by you coat the wires with some plastic, rigid plastic that holds them apart. And you've seen this type of line that comes with FM receivers. We call it a twin line. Twin meaning you have two conductors. And you've seen this sort of thing. You get what's called a folded dipole, which is twin lead that is shorted at the ends. And then you have the line, it tees, and then it comes down, you hook this to your FM receiver. This is called a folded dipole. And it's just made out of twin line. Now, I'm not going to derive the formula. I'm just going to give you the equations and work with those for capacitance, inductance, resistance, and inductance of a two-wire transmission line. Let's say we have two conductors, both of radius A, and their separation distance is D. That's the center-to-center separation distance. The capacitance per unit length, I'll denote it that way, capacitance per unit length is pi epsilon over the inverse cosine of D over 2A. And this is approximately equal to pi epsilon over the natural log of A over D, or D over A. And this is for the case when D is much, much greater than A. That is, the separation distance is much larger than the size of the conductors. For the line, the external inductance, there's several inductances that we need to look at. There's the external inductance, which is mu over pi, where this is the permeability of the medium between the two conductors. And this is the inverse cosh of D over 2A, which again, if D, the separation distance, is much greater than A, it's mu over pi times the natural log of D over A. Now, there's an internal inductance on the line, which is a self-inductance, because as you have current flow in a line, these current magnetic fields set up by each of these individual current elements couple all the other current elements, and it gives rise to a mutual self-inductance of internal to the wire. And this works out to a very nice number. This is mu over 8 pi which is 500 or 50 nanohenries per meter, which is about 1.27 nanohenries per inch. That's the self-inductance of a single conductor due to current flow internal to the wire. And then at high frequencies, the inductance at high frequencies is mu over pi. You combine these two plus another term. If I pull out a mu pi, the internal inductance is 1/8 plus the inverse cosh of d over 2a, and then there's another term that you end up getting due to skin effect. That's what delta means. That's the skin effect of a conductor that's related to the frequency and the conductance of a wire. Our sigma, it's 1 over the square root of omega mu sigma, where mu is the conductivity or the permeability of the material that composes the wire, and sigma is the conductivity of the conducting wire, and omega is just 2 pi times the frequency of operation. So this gives you a pretty good value for the high frequency inductance of a conductor or of the two-wire transmission line. Now, two other important values is the resistance per unit length, which is 1 over pi a delta sigma, where this is the conductivity of the conductor, and again our delta is the skin effect. This is called skin depth. I'll get into that in another lecture. What this basically relates to is that as the frequency of operation of the signal that you're trying to transmit down the wire becomes larger and larger, the self-inductance of the current elements tend to push themselves out towards the surface. And if the frequency is high enough, there actually isn't any current flowing deep inside the wire. It's all flowing on the surface of the wire, and the depth at which the current density within the wire falls to 1 over E compared to the surface current, the value of the current as you enter the wire, as it falls off by this amount, 1 over E, that's called the skin depth, is that distance at which the surface, the current density within the wire has fallen off to 1 over E of the surface current. And then our conductance per unit length, that is, if there's some losses, resistive losses in, or dielectric losses in the material that's separating the two wires, the conductance is the inverse cosh of d over 2a times 2 times the conductivity of the wire. Now, an important relationship here. I'm only going to be concerned about the low frequency values. And that is these values here for inductance and capacitance. Our inductance per unit length and capacitance per unit length. And notice, you see, the inverse cosh appears in the denominator of the capacitance and in the numerator of the inductance, and they have the same value. This is a geometric factor. Look what happens if we take a product of C times L per unit length. what we get is epsilon times pi times the inverse cosh times mu over pi times the inverse cosh. And those cancel and the pi's cancel and we get mu epsilon. An extremely important relationship in transmission lines. And you'll find this true for any transmission line that is operating in what we call TEM mode, transverse electric magnetic. That is, we have plane waves that's propagating in this direction, say, and our electric and magnetic fields let's see, E cross B, yeah, okay. So if our electric field, say, is in this plane, our magnetic field is at right angles and transverse to the direction of propagation. It's propagating with the direction, in a direction V. That is, we don't have any electric or magnetic fields axial in the direction or in the direction of propagation. They are transverse to the direction of propagation. That's what we mean by TEM mode, transverse electric magnetic. So the capacitance per unit length times inductance per unit length is a constant. It's equal to the permeability times the permittivity. The geometric factors drop out. It doesn't matter what the geometry of the transmission line is. Whether you have, say, a coaxial line, a two-wire line, or, say, a square conductor type coaxial arrangement, it doesn't matter. The product of the capacitance per unit length times inductance per unit length is equal to this constant. And so if I write, see, let's write these equations a little bit differently. We can see that our capacitance per unit length is epsilon divided by a geometric factor, and the inductance per unit length is equal to mu times the geometric factor. And these geometric factors are the same for the conductance and inductance per unit length. Now, it turns out that inductance is a lot harder in general to calculate than capacitance is. So if you wanted to know the inductance per unit length on a transmission line or in some structure where you have a uniform cross-section per unit length, all you have to do is compute the capacitance. And then, using the geometric factor, you can get the inductance directly from the capacitance, because we can see this, that if I solve this for the geometric factor, we have mu, and then solving for geometric factor here, this is epsilon over c per unit length. So we have mu epsilon over c per unit length, which we had already written, right? L per unit length times c per unit length is mu epsilon. So if I compute the capacitance per unit length, then I get the inductance per unit length directly from that. And generally, like I said, it's easier to compute the capacitance between conductors in a structure of uniform cross-section than per unit length than it is the inductance. So you can use that relationship. Now, I'm going to give you another useful relationship that is useful when computing stray inductances in a network or a circuit. It gives you a good starting point if you want to approximate how much stray inductance you have. Let's look at our two-wire transmission line. I'm going to just rotate it 90 degrees. Both conductors have the same radius. We'll call it A. But we know from the way that the fields behave in two equal diameter conductors is if we were to look at the electric field and plot it, the electrostatic field, it'll look like this. The significance of this is if we have a potential difference between these and we plot the potential field, the equal potential surfaces are going to look like this. And right at the midpoint, we have a potential surface there that's, in this case, vertical. And if we make this a zero voltage potential field and say apply minus V to this conductor and a plus V to this conductor, or say V over 2, so that the overall potential difference is V, right at the middle, it'll be a zero potential. So what we can do is put a conductor there. And it won't change anything. And we can ground this conductor. And if we place a plus V over 2 voltage on there with respect to the conductor and a minus V over 2 potential with respect to the conductor, the field plot is going to be exactly the same. The field plot here will look like this. So nothing will have changed. Why is that significant? It's because the two-wire transmission line is exactly equivalent to just one conductor above a ground plane. Remember, we had a separation distance here of D. Now if we say we have a height h above the ground plane, then h is just d over 2 in the equations that we had. So the inductance per unit length that we had is mu over pi times the inverse cosh, hyperbolic cosine. In this case, it was, remember, it was d or let's see, it was d over 2a for this. The inductance per unit length was mu over pi times the inverse cosh of d over 2a. Well, the relationship d over 2 is just h. So for a single wire above a ground plane, a conducting ground plane, you'll have this relationship. So this gives us a relationship for a wire above a ground plane to compute its inductance. Now, let's get a handle on these values. Right here, our inductance per unit length is permeability, mu, times the inverse cosh of h over a. Now, for the values here, let's assume we're in free space, that we just have air between the ground plane and the conductor, so our mu becomes mu 0, that is, the free space value, which is 4 pi times 10 to the minus 7th henries per meter. And if we put that value in here, then our L per unit length, we have 4 pi times 10 to the minus 7th divided by pi, or 0.4 microhenries. So this will be 0.4 times the inverse cosh of H over A microhenries per meter. Now let's look at inverse cosh. If here are my y values, here is the inverse cosh of y. And in this case, y is equal to the relationship of the height the wire is above the ground plane, the center of the wire is above the ground plane, to the diameter of the wire. That's what H over A is, or my y value. So if y is 0.1543, the inverse cosh is 1.00. 2, we get 1.317. 3, it's 1.763. 4, it's 2.063. 5, it's 2.292. 6, it's 2.478. 7, it's 2. Yep, someone calling me, but I'll have to ignore that for now. Let's see, 7 is 2.634. 8 is 2.769. 9 is 2.887. And 10 is 2.993. Now, if we plot this, if we have, this is 1, 2, or let's write it this way. 2, 4, 6, 8, 10. And this is 1, this is 2, this is 3. Now, if I to plot this out, when and at 3, we're at about 10. It's a slow rising function. I've rewritten the board. We're looking at a single wire above a conducting ground plane. The wire is a height h above the ground plane, and the wire has a radius a. The inductance per unit length we've shown to be 0.4, the inverse cosh of the ratio of the height the wire is above the ground plane to its radius of, and gives us microhenries per meter. Okay, y is a ratio of h to a. The inverse cosh of y is this value. We see that it's a very weak rising function with y. It looks a little bit like this. We go from a y of 1.5 to a y of 10, and the inverse cosh only changes from 1 to 3. Now let's just kind of focus on the inverse cosh in this region here, where the h to a is the height h is 4a. That's the minimum value, and it's going to go to h equals 10a. So on the lower value, we can see, since the radius of the wire is a, then the bottom of the wire will be 3a, 3 wire radiuses, or 1.5 diameters above the ground plane, when the h to a is 4. And when H to A is 10, it will basically be 4.5 diameters. The bottom of the wire will be 4.5 wire diameters above the ground plane. Now, let's get a handle on what the inductance of the wire will be. Well, if 4 is less than or equal to H over A, which will be less than or equal to 10, this is our Y value, then the inverse cosh is going to go from 2 to 3. Okay? From here to here. Now using that, if we multiply through by 0.4 to get the inductance, then the inductance goes from 0.8 microhenries to 1.2 microhenries. So this gives us a bounds that when we go from a height of the wire of 4 wire radii or 2 wire diameters above the ground plane to 5 wire diameters above the ground plane, the inductance goes from about 0.8 microhenries to 1.2 microhenries. And a good starting point, the value I always use for a wire above a ground plane, gives you a single wire above a ground plane, conducting ground plane. You pick up an inductance of about 1 microhenry per meter, or 1 nanohenry per millimeter, or 25 nanohenries per inch. That gives you a pretty good starting value for using to determine the inductance of wires above a ground plane, like lead lengths of resistors, capacitors. You're going to get on the order of about 25 nanohenries per inch, or 1 microhenry per meter. And that gives you a really good starting value, and it works out very well in practice. I've measured lead lengths of resistors and capacitors and wires above ground plane, and they always come within this value, right around 1 nanohenry per meter. So the theory indeed does predict it correctly. So this is a good starting point right here. Now, a couple interesting relationships that you might want to keep in mind here that we talked about and I'll further discuss is, we know that the geometry factor is the same for inductance per unit length as capacitance per unit length when we're talking about 2-wire transmission lines and transmission lines in general. We know that the inductance per unit length times capacitance per unit length is equal to mu epsilon, the permeability times the permittivity of the medium in which the conductors are immersed in. Now, if we're in free space, then mu is mu0, which is 4 pi times 10 to the minus 7th henries per meter, and epsilon becomes epsilon 0, which is 10 to the minus 9th over 36 pi farads per meter. And the product, mu0 E0, becomes 4 pi times 10 to the minus 7th times 10 to the minus 9th over 36 pi. You see that 4 pi goes into 36 pi 9 times. We get 10 to the minus 16th over 9. Let's look at the square root of mu0 E0. That becomes 10 to the minus 8th over 3, or 1 over mu0 E0 equals 3 times 10 to the 8th, and this is a velocity. This is meters per second. And what is this? This is the free space velocity of light. 300 million meters per second. Velocity of light. So in general, a wave, TEM wave, propagating down a transmission line is equal to 1 over mu epsilon. And if we write mu as mu 0 mu sub r, relative permeability, and permittivity as E0 times relative permittivity, this becomes C over square root of mu sub r E sub r, and I'll call this C0. This is the free space value of the speed of light. And as we see on a transmission line, if we have a dielectric material between the conductors that's greater than 1, E sub r is equal to 1 for free space, the velocity slows down. And that's in general true for transmission lines, is that the propagation of an electromagnetic wave, TEM wave, down a transmission line is always slower than the free space value. Another relationship for transmission lines is that the characteristic impedance we call Z0 is the square root of L per unit length over C per unit length. So if I know my resistance or my inductance and capacitance per unit length, then we can get the characteristic impedance of the line. Well, remember that we had a relationship between inductance and capacitance with the geometric factors, is that L is mu times the geometric factor, and C is epsilon divided by the geometric factor, so we have the geometric factor squared. Or the characteristic impedance of a line is its geometric factor times mu over epsilon. So the velocity on the line, the characteristic impedance of the line, depend on the geometry and the properties of the dielectric between the conductors. If, say, we have a transmission line, let's say a coaxial line. Well, it turns out 50 ohm coax, like RG58U, has an inductance per unit length of 75 nanohenries per foot, and the capacitance per unit length is about 30 picofarads per foot. So if we put the numbers in, say for Z0, let's say Z0 squared is L over C, so we have 75 times 10 to the minus 9th henries per foot, and we divide by 30 times 10 to the minus 10th farads per foot, and 30 goes into 75, 2.5 times, and this is times 10. We bring 10 to the 12th up, so that's 10 to the 3rd, or we can write this as 25 times 10 squared. That's Z0 squared. So Z0 then is the square root of this, which is 5 times 10, or 50 ohm. Length, we have L per unit length times C per unit length equals mu epsilon. Now the velocity of propagation on a transmission line is 1 over mu epsilon. We already discussed that. And if we have the free space values of mu and epsilon, we get the speed of light. Now the speed of light in a transmission line is related to its inductance per unit length and its capacitance per unit length. Let's put in these values. The 75 nanohenries per foot on RG58U is 246 nanohenries per meter, and the capacitance per unit length of 30 picofarads per foot is 98.4 picofarads per meter. So if we put that product in here, 246 times 10 to the minus 9th times 98.4 times 10 to the minus 12th, this comes out to 203.2 million meters per second. So I'll write this 10 to the 6 meters per second. Remember that the free space value, V0, which is speed of light in a vacuum, is 300 meters per second. So we see that the velocity of light has slowed down as it travels down a coax to 203. This is 66% of the free space value. So on a coaxial line of RG58U, the velocity is 66% of the free space value. That is, 203 divided by 300 is about 66%, 67%. So this is generally always true with any sort of structure where you have dielectric constants that are different than the free space value, and we can get what the dielectric constant is from this, knowing that the ratio of the velocity on the coaxial line compared to free space is only due to the permittivity difference, because the mu, or the permeability of the dielectric material that separates the conductors on a coaxial line, tends to be like polypropylene, a foam type dielectric, and the mu is equal to the free space value. That mu sub r is equal to 1 on these types of lines. So this difference in speed is due to the permittivity, or the dielectric constant, of the material inside the coaxial cable that separates the two conductors. And if we have 0.67 or 66%, if we square that and ratio it, we get a dielectric constant of about 2.2, 2.18. So our E sub r would be about 2.18. That's a dielectric constant of the material that separates the conductors on a coaxial line. So I kind of give you a brief overview of the relationships on a transmission line. I'll get more into that later as I do modules on Maxwell's equations and the propagation of electromagnetic waves in space, and guided waves on transmission lines and conductors.